Okay, I'm very glad to be here, and I'm going to. My area is actually in statistics, so today I'm going to present some recent work with my previous student on support vector machine for classification. So, but here we consider the case that the data size is very large, so that we need to spread it onto different machines for analysis. So I'm mostly interested in some theoretical aspects of this method. So first, although probably most of you already know what is support vector machine, but I will give a brief introduction first. So the problem is, for classification we have x and y. So we use x to predict y. Here is classification, so y is only two classes. So we use -1 and 1 to represent the two classes. The dimension of x probably is high dimensional, so p is very large. So it's p-dimensional covariance. So support vector machine says that, okay, so if we have two classes represented by different colors here, a separating hyperplane we should use is the one such that the closest point to the hyperplane is the maximum. So in this figure, there are 3 points that are closest to this hyperplane, and we choose the hyperplane such that the distance of these points to the plane is the maximum. Mathematically, this is formulated as this. So we maximize over the different hyperplanes, so which is characterized by beta and b, the intercept b and the slope beta, and we want to choose the hyperplane such that we maximize the distance of the closest points. So this is maximum on the outside and minimum problem on the inside. So so this problem here can be written in a slightly different form. We just minimize the norm of the beta here, but we square it for differential for it to be differentiable, and we constrain that the points to be on the correct side. So that's why if you have the hyperplane, you multiply by either 1 or -1, which is yi, you constrain it to be positive. So this 1, the number 1 is arbitrary. So this is just the original motivation for defining a support vector machine. This works only in the case that the two classes are separable in the sense of this figure. So you can find the hyperplane that cuts the plane, cuts the space so that you perfectly separate the two classes. More generally, we have this kind of formulation. We relax the constraint so that we don't require that this product between the class label y and the equation for the plane to be always positive. So we constrain it to be bigger than 1 minus some number, but this number we constrain it to be we want it to be as small as possible. So we minimize also this sum over this relaxed variable. Still the norm of beta is still here. So this is the usual standard formulation of support vector machine in a linear case. In statistics, we don't like this formulation. It works well if you want to optimize it, because you can. There are lots of ways to deal with constraint optimization. A lot of efficient algorithms have been designed. But for theoretical analysis, we slightly prefer a different formulation by transforming the constraint optimization to an unconstrained one, just by combining the constraint with this sum into this form. So it's not too hard to see these two formulations are actually the same thing, because in order for the constraint to hold, usually we have equality. Okay, so why do we like this kind of formulation? Because in statistics, we usually think of any regression problem to have a loss function. We are minimizing the loss. So the second term here can roughly be regarded as a loss. It's always non-negative. And it penalizes more if the sign of the class label and the linear function is different. So we want the linear function to predict the label. So ideally, we want these two to have the same sign. But if they are different, we penalize it. And this square of the beta norm can be regarded as a regularization term in the sense that we want to control overfitting. Okay, anyway, now we have this kind of formulation, which the second term is a loss function. The first term roughly can be regarded as a smoothing term. Okay, so now we just, because for conventional reason, we just switch the position of the two terms. So we write the loss function first. So the loss function, we use capital L to denote the loss function, which is just the function written on the previous slide, plus some square of the norm of the beta. So this particular loss function is called the hinge loss. Now in 2003, Zhu and others says, okay, in high dimensional case, I don't want this square norm because the only purpose it seems that the square norm is doing is that it's trying to prevent overfitting. But suppose in the high dimensional case, we also want to do variable selection. Now a very popular method is called lasso. Just by changing this square norm to be a one norm. One norm is just the sum of the absolute value of the components of beta. Okay, so once you change from this square norm to this L1 norm, it can automatically shrink the different components of beta to 0. So if after you optimize, you find that some components of beta is 0, that means the corresponding component of x is not affecting the prediction. So the advantage of using L1 norm is that it can do variable selection automatically. Okay, so in this work, we just focus on this formulation on the last line. Our interest is first, what's the property of the minimizer, assuming the dimension is high, and second, how to do divide and conquer if the sample size capital N is very big. Because optimizing this, you can do, of course, but if N is very big, it's not feasible. Okay, so just let's look at the standard case first. We just try to solve this problem with L1 penalty, L1 norm on beta. First, we want to study the asymptotic property in statistics, probably unlike other disciplines. The first thing usually we do is to study, if you minimize this, you get something called beta hat, which is an estimator of beta. And then we want to study how fast beta hat converge to the true beta. Okay, so doing asymptotic analysis in statistics is usually standard, except that here we have some a little bit of technical challenge in the sense that the loss function here is not differentiable. Just at one point, not a big deal usually. So remind you what's the shape of this loss function. It looks like this. If this guy is positive, it's just this linear function. Otherwise, it becomes 0. So in figure, it becomes this blue line. So at one point, it's non-differentiable. Usually in statistics, when we do asymptotic analysis, we need to take derivatives. Very simple technical stuff just to take the expansion. So we usually need to expand it to the second order term. So we need to take two derivatives. First, we define the true, actually the target of estimation to be beta 0, which minimizes the loss function. We assume it exists and unique and is also sparse, meaning that there are lots of zeros in beta 0. Okay, so we need to take derivatives. So the first derivative S, the gradient function called S here, where you get two linear functions connected together. You take derivative, of course you get the indicator function. The one point that's not differentiable, that doesn't play any role here. You just get an indicator function here. But when you take second derivative with respect to beta, which is the Hessian matrix, the delta function appears, which causes some technical trouble in analysis. But still we can do it. Okay. Now, a more important aspect of this model is that later when we do divide and conquer, for now we don't do it, but later we will do divide and conquer. But when you have L1 known penalty, the trouble is that the estimator is biased because of the shrinkage by the L1 known penalty. So we need to study the bias. In statistics, bias is just, if you have beta hat, what's the difference between expectation of beta hat and the truth? There is a bias when you have L1 penalty. Okay, so in order to look at the bias, we first take derivative of the objective function we are trying to minimize. We get the first order condition, which should be straightforward. So at one point it's not differentiable, so that's why we have subderivatives, subgradient, etc. But it's just the first order condition. Now, as I said, when we want to do asymptotic analysis, we need to take another derivative, take second derivative in order to get some asymptotic property of beta hat. So, but the trouble is that we cannot differentiate it. So in statistics, we come up with this. People come up with this idea of using empirical process, which just means when you have something that's not differentiable, we replace it by the expectation. The loss function is not differentiable. In particular, the second derivative. The first derivative is okay, except for one point, but second derivative you cannot do. You have a jump. So empirical process just say, okay, let's replace the average by expectation. Expectation of something not differentiable can be differentiated, actually, because expectation actually is an integral. So integral has a smoothing effect. So that's just what empirical process says. We have something not differentiable, so we replace it by the expectation here. Now expectation can be differentiated, so we get the Hessian matrix. Now this equation, if you look at the left hand side and the right hand side, this is just what statisticians usually do when we do asymptotic analysis. We do expansion, so beta hat minus beta 0 comes out on the right hand side. So we just multiply both sides by the inverse of the Hessian matrix. You have an expansion of the difference. All right. Now from this kind of expansion, it's also easy to see what's the bias. Actually, the bias is just the left hand side. When you don't have the L1 penalty, the left hand side is 0, right? Because you only have loss function, you take derivative of the loss function. The first order condition says the derivative on the left hand side is 0. But now you have penalty, so you have an additional term which is just the bias. So bias actually come from the left hand side. So as I said, I want to debias this estimator beta hat. So what we do is very simple, just subtract the left hand side from beta hat in some sense. After you take inverse of this Hessian matrix and multiply to the left hand side. Okay, so this is what we do. Originally, when you try to solve the optimization problem with a lasso or L1 penalty, you get beta hat. Then I subtract the bias, which is this guy here. I get beta tilde. So hopefully, beta tilde is a more accurate estimate than beta hat in the sense of bias. Now, of course, the problem is that here, the technical problem is that we cannot directly take the inverse of the Hessian. The Hessian is defined. First, beta 0 is unknown. It's a true value. But you can estimate it by beta hat. No problem. The second problem is that the Hessian matrix is unknown. What's Hessian matrix? Is the second derivative of the expectation of the loss. Now, of course, expectation is unknown. You cannot just calculate the expectation in statistics. You only have data. But expectation can be approximated by average. Everyone knows that this is a trivial step. Expectation can be approximated by average. So it seems that the Hessian can be estimated, except for one small further step we need to deal with. Trouble we need to deal with is that the Hessian matrix, as I said, as you saw before, involves the delta function. So how to estimate the delta function? So in statistics, we do smoothing. We smooth out the one point that's undifferentiable. And then, of course, theoretically, you need to prove that the smoothing doesn't cost you too much, which we can do. So how to do smoothing? The method is very easy. You just, instead of a delta function, I replace it by a density. A density that has a peak at 0. Okay, so here Q is a density. You can use any density, but of course the standard choice is the standard normal density. Okay, so you can estimate the Hessian matrix, but now we need to take inverse of that. And this is a high dimensional matrix, P by P high dimensional matrix. The sample size is n. Suppose we say, okay, P is bigger than n. The rank of this matrix H hat, the estimator, means that if P is bigger than n, you cannot invert this. So we need to insert another piece of method to invert this H hat. So actually we use some existing method that says that if you assume that the inverse of the true Hessian matrix is sparse in the sense that many of the components are 0, then we can still estimate it. Even we can still somehow take the approximate inverse of this H hat, although it's singular. So there's a way to do it. So the way is this. Instead of taking the inverse, we constrain, we say we want to estimate theta, which supposedly is the inverse of the Hessian matrix, but we don't directly take the inverse. We say the product of this inverse with H hat is close to the identity. And we minimize the one norm of the matrix. So in this case, we can get an estimator of the inverse of the Hessian matrix. Okay, so we put everything together. We can show some theoretical result. Okay, the main result is here, which says that after you debias the beta hat, you get beta tilde. So the error in terms of infinity norm of this vector is actually this enormous guy, which actually the main term is just something in the middle is square root of log p over n. The other can be assumed to be small, so it's just the guy in the middle, square root of log p over n. This is the convergence rate. This rate is in some sense optimal, not exactly optimal, but this is the rate usually people accept for this class of problems. Okay. Okay, now I really come to the divide and conquer part. So now we assume that, okay, previously we can calculate beta hat, beta tilde feasibly, but if the sample size capital N is very, very big, so big such that we cannot do it. I don't know how big, because in the audience probably many of you can deal with extremely large data sets. What I'm saying here, tens of thousands is nothing to you, but that's the biggest I can deal with. So suppose N is very, very big. What we can do is that suppose we have M machines, we can just randomly partition the data into different M parts and throw the different parts onto different machines. And each machine can carry out the calculation independently using only the subdata. Okay, so the size of the data at each machine is of course capital N over capital M, denoted by small n. So each machine deals with a subset of the data. Now on each machine independently they get some estimate of beta. So we use superscript to denote the estimate obtained by different machines. So you have beta hat, beta tilde. Then at the end, you average everything. So a central machine collect the results from different machines and say I just want to average the results obtained by different machines. So in terms of concept, this is trivial. Right? Everyone knows you can do that. It's just the theory is a little not so trivial. Okay, so at the end, you average the estimate from different machines, you get beta bar. So this is our the estimator we want to investigate. So what's the property of beta bar? So at the end, we show that under some conditions, the aggregated estimator beta bar still has convergence rate as before. As I said, the main term is square root of log p over n. So same as before. So at least in terms of convergence rate, we don't lose anything. We don't lose much. Okay, so this is the main theoretical result of this work, showing that if you just split data onto different machines, then you do debiasing, then you aggregate the estimates, you get an estimator with the same statistical property. Okay, so this corollary just says because the previous one has very complicated conditions, so we simplify it a little bit. Note that the main condition of interest may be here, so the number of machines cannot be too large compared to the sample size. Otherwise, the procedure will fail. We have this convergence rate. Okay, now there is one last step left, is that, okay, previously the reason we want to do L1 use L1 penalty is that we want to do variable selection in a high dimensional case. But after we debias it, or we subtract something, then nothing is sparse. So no components of beta are 0. We take average, still it's non-sparse. So we still want, if we still want a sparse estimate, we want to do variable selection, we can do a thresholding step. So if you look at the components of beta one by one, if it's large enough, we keep it, otherwise we set it as 0. It's just a truncation, a thresholding, very simple. And theory says that if we choose the threshold appropriately, you still get the same convergence rate. But of course, in practice, how do you choose this threshold is a problem. we use a very heuristic procedure later. Okay, so let's look at some simulations to see whether this procedure works. Now I'm not going to say most of the so we have several procedures. One is the central estimator. It's just that you use all the data. We don't choose sample size so large. It's just simulation. So we still have sample size that we can manage. We have aggregated estimator without using bias correction. So each machine estimate beta, then take average. The third one is our procedure. You do debiasing, then you take average. But you don't do the last step of thresholding. Then the fourth one, it does thresholding. So we compare these estimators. So I quickly just go over the simulation result. So we choose n equal to 20,000. By modern standard, this is probably non-impressive, but this is the largest I can manage, almost. We choose the number of machines from 1 to 30. The dimension is 5,000. So in these figures, it shows the errors of the estimate using different errors. The first one is the error in terms of L infinity norm, then L2 norm, then prediction error. So I just look at the prediction error. So this shows, so the x-axis is the number of machines. It says that, okay, of course, if you can compute it, you use one machine. If machine increase, number of machines increase, the error becomes bigger. Then the red one is the one without using debiasing. You just, each machine use sub-data to compute beta, then you aggregate by taking average. So this shows it doesn't work as well as the blue one, which is our final estimator. You use debiasing, you take average, then you do thresholding. So this just shows that the debiasing actually is necessary for this procedure to work. We also do some slightly larger sample size, not too large. So this shows us as the sample size increase, what's the performance of this. I'm not going to say anything except there are a lot of lines here, but the only thing I want you to look at is just the black line, which is the central estimator. So it's the standard. You use all the data. So of course it's the best if you can compute. Our estimator is the blue one, which is hidden behind the purple one. I'm not going to tell you what's the purple one. So, but it's just the blue one hidden behind the purple one. It says so. This shows that our estimator still perform very well. The red one, as before, is the more naive estimator that you use. You don't do debiasing. You just simply take average. So it doesn't work as well. Okay, so that's all I want to say. Thank you.
So time for questions. I have a comment on the conversion rate. One of those letter N.
Yeah.
From your formula that you wrote there, it sounds like that's ensemble average or MC Monte Carlo average. So that's the optimal. You cannot do better than 1 over square root N. That's the.
Yeah, in a fixed dimensional case, yeah. Without extra assumption, we cannot do better.
Yeah, that's the best you can do.
Yeah.
From Monte Carlo point of view. Another comment that I have is that you actually start from L1 and then you compute the gradient and then you compute the Hessian and then you actually modify, you actually smooth out in order to compute the Hessian, right?
No. Yeah, you need to the smoothing is only done in order to compute the Hessian.
I know, that's what I understood. My question is that you actually can, or athlete one can actually smooth the original L1 problem, right? The L1 norm, you just add an epsilon, right? The L1 norm of a vector is a summation of the absolute value of.
Yeah.
So you can summation of the square root of each of the components where plus some epsilon.
Maybe, yeah.
I mean that's actually quite popular in the English problem community. When you have TV photo variation realization, you can add little epsilon to smooth out that one point.
Mm-hmm.
Right? And as soon as you include
Yeah.
that, you can take the gradient. And
Yeah.
So
Yeah.
any problem.
Yeah.
It's just common that you can do from
Yeah.
and you
But
can avoid subgradient,
yeah. Operationally, you can do that. But I don't know. In statistics, we tend to do the other way. Somehow. Yeah. Yeah, the aim is to prove some theoretical result. Not numerical convergence, but theoretical convergence. Yeah. Yeah.
Another thing is that when you have the improved beta kilo equal to beta 0 minus n Hessian times the ensemble average of the subgradient, it looks like Newton step to me.
Oh, we just do one step. Yeah, sort of. Yeah, sort of. Yeah, I didn't realize that, but sort of like that. But we just do one step. Yeah.
Instead of having this usual one gradient and then you have an ensemble gradient, and you have an ensemble Hessian, which you do approximation. So my comment is that you can make the quite large error in Hessian, yet you still can get the good white, because in optimization, right, as soon as you have the gradient correctly, the Hessian you can approximate quite roughly, and yet you still have the good.
Yeah, you may be right. Yeah.
But that's why that's also an explanation. You can approximate Hessian in methods to work with, because assuming the gradient correct, that's all matters for Newton approach and optimization.
Yeah. Thanks.
Okay, let's send the speaker again.